So if you are online, please signify. Let's know whether you are online. So if you are online, please signify. Let's know whether you are online. Let's know whether you are online. So let's quickly look at something that we can quickly do before the network goes off. So what we are going to be doing is just what I planned, like just having a physics at glance, physics in a glance. So let's quickly look at something that we can quickly do before the network goes off. So I hope you understand. So let's start. So physics at a glance, we have some areas that you need to know in physics. Now, okay, let me quickly brainstorm. Okay, let's do uh some areas in physics that you need to quickly know. Don't forget that we have machine, we have types of machine. Types of machine are lever. What again? We have the pulley. What again? We have the hydraulic press. What again? We have the what again? We have the gear wheel, and so on and so forth. So you need to know the formula for all these things. I hope you understand. So you need to know their formula. So most of them, they have formula for their velocity ratio. I hope you understand. So just know them. So let's quickly do some chemistry. I plan to do chemistry, though it is physics revision note, but I do chemistry. Now, let's quickly do law of solubility because of the network issues that we are having. That's why we quickly want to do something that is reasonable. So what we are doing is, what is that? Law of solubility. So you should know it that all sorts of sodium, potassium, and ammonium ion, they are what? They are soluble. Please take note of that. Then also all sorts of NO3. Whenever you see NO3 in a salt, it is what? They are all soluble. Just know that. Hope you understand me. So that's it. Just know that. So it is automatic. Then you should also know that all sorts of chlorine are soluble, except, so there is exception there, except AgCl, PbCl2. I hope you understand that. So if you are online, please signify at the comment section. Please signify so that I can know. I don't like using black color, but let me continue with this since that's what I started with. I don't like using black color. So let's quickly continue now. So all sort of chlorine are soluble except the salt of HCl, PbCl2, and HgCl that are insoluble. So please take note of that. I hope you understand me. So you need to know this law of solubility, and also you should know that all sorts of CO3 are insoluble except those of sodium, potassium, and ammonium. Now if I ask you, this salt NaCl, is it soluble or insoluble? So if you know it, drop it at the comment section. I want to know if you really know it. Then also, oh sorry, it's not that anyone is online, I'm the one online, so that's why I'm having one views. I hope you understand. So it's not that the person is online. So okay, sodium chloride. So because I'm using this, I'm using my phone as a test run so that I can know if there is really network. So sodium chloride, that's, I told you any salt that has sodium, it will be soluble. So that's the answer. Now, will this be soluble? You can drop it at the comment section. Though I told you CO3, every sort of CO3 is insoluble, but because it has sodium, it will still be soluble. What of this? And also, I forgot to tell you this. All sorts of SO4 are soluble, except all those PbSO4, so I think CaSO4 also, and so on and so forth. So they are insoluble. So it means PbSO4 is what? Insoluble. So these are part of the things you should know. And also, don't forget, don't mind my voice, I can't speak it louder. So I think I'm audible enough, because I don't want to, it's in the night already, I don't want to be shouting. Now, what is the uses of this law of solubility? It is used in separation techniques. So that's where we normally use law of solubility. We normally use it in what? Separation techniques. And that is filtration. So filtration, it involves, it is used in separating soluble and insoluble salts. You should know that. So this is the apparatus for filtration. If they ask you to draw to, no, they cannot say you should draw it in Jamb, because Jamb is CBT. So except in WAEC. So this is how you have it. Mind you, I'm not taking any book with me. I'm just doing everything offhand. So you pour the salt here. Now, this paper, this is a filter paper. Now, you are going to be having the soluble salt is going to be coming out as the what? As the, don't let me use something like that, as a liquid, clear liquid, because it will have dissolved in water. Because this is how to do solubility, filtration. You will dissolve the soluble and insoluble salts together. I hope you understand. You dissolve them. So after you now dissolve them, the one that is soluble we you won't see it again very well, because it would have dissolved in water. While the one that is insoluble is going to float. So that's why we normally call the one that is on the top residue, while the one that is below, we call them filtrates. Hope you understand. So this is the funnel. and this is a beaker. So you can see it's very easier. That's all. They ask you to draw the apparatus for sublimation, so you just draw an inverted uh, funnel. Then you draw your evaporation dish. That's all. Then you draw your heat source. So diagram is very simple. Just know what they are used for. You put your retort stand, put everything here. So this is the diagram for sublimation. And I told you we have sublime substance. So what are the sublime substance we have? We have the ammonium chloride. So most of the time in practical chemistry, ammonium chloride is frequently used as experiments. Though we also have other supply substances like sulfur, camphor, etc. So you need to jot everything down. So this is a funnel. Now the sublime substance will be in this place. So after it is the heat source is supplied to it, after some time, the heat source after it is supplied to it. So assume this is it. This is the fire. And after it is supplied to it, so the sublimate is going to be forming here. Though you know that sublimation means solid to gas, right? Solid to gas, right? And this is a solid, so it will go in form of vapor to this side. So after getting to the funnel, it's going to become a solid. So you have to scratch it from this surface, so it will become solid again. Hope you understand. So that's the diagram for sublimation. Now let's go to separation technique. Separating funnel, though I don't plan to do this, but I don't just know what directed me to this place. So I'm just doing like a glance for chemistry. So separating funnel also is very simple. Just draw your diagram like this. If they ask you which what is it used for, it is used. So you just draw your retort stand. Draw it here. Don't mind my diagram. Though it shouldn't be like this. I made a mistake. So you put your tap here. So you put your beaker to collect the something. So you now do it like this. So you put it like this. So you use it to hold it, the retort stand. So you just put it like this, So I hope you understand. So that's it. So I hope you guys are hearing me very well. So when you are watching this video, just be dropping your comment. That's the physical properties used, different densities. So example of such liquid is when we have petrol and water. Petrol and water cannot mix. So I hope you understand. So petrol and water cannot mix. Then water and kerosene also. That's also another scenario. Water and kerosene. So if we are to separate them now, one of the layer will be on the top, while other will be on the bottom. So the one that is on the bottom, you will run it through the tap. After it drop through the trap, then when it reach this layer, then you close the tap, so that means you have separated the lower layer. So the lower layer, the reason why it comes down is because it has high densities, while the one on the top, it has low density. So that's just it. That's the properties they use. So if they ask you what is the properties used for separating funnel, it is used for liquid with different density. So that's the properties used for separating funnel. I hope you understand. So that's just it. I hope you are gaining something. I hope it's not a waste of time. Let's continue. So another thing you still know is, you know that we have other methods, but let's just leave it here. Let's move to some aspects. Now there is something you need to know, that we have two strong acids for your own level. though we have more than that, which are we have three strong acid rather, H2SO4, HCl, and we have HNO3. H2SO4 is tetraosulfate 6 acid, HCl is hydrochloric acid, HNO3 is triazonitrate 5 acid or hydrogen triazonitrate 5. So now strong base also, we have two strong base, so we have more than that, but for your level, so just stick to 2. So we have KOH, we have NaOH. Now in acid base and salt, there's something we call choice of indicator. So we have some common indicator, though we have many of them, but for your level, don't just stick to phenolphthalein. Just stick to phenolphthalein, methyl orange. I don't want to make everything complex for you. Just stick to methyl orange, phenolphthalein, and that's all. Let's just limit it in that scope. Do you get? I don't want to make things complex for you. So do you get? So I don't want things to be complex for you. Now there's something we now say when we have strong acid and strong base, when they are being titrated. You know that titration is the process whereby acid and base is uh, is kind of mixed together. So when then we use indicator to so if they ask you what's the meaning, what is the uses of indicator? Indicator is used to detect the end point or the point at which the total amount of acid has titrated the base. I hope you understand. So it is used to determine the end point. I hope you understand. So that's the uses of an indicator. Now you then now say when we have strong acid, strong base, which indicator are you going to use? Whenever you have strong acid and strong base, you are free to use any indicator. Though we have more than these two indicators, but just for your level, just stay with it. We have methyl red, we have litmus paper. What else? We have Congo red, and so on and so forth. But for this one, let's just leave it at this scope. So now in this strong acid, strong base, you are free to use any indicator. Any indicator means if you use methyl red, you are correct. If you use litmus paper, you are correct. If you use Congo red, you are correct. If you use phenolphthalein, you are correct. If you use methyl orange, you are correct. So that's what I mean by what any suitable what indicator. Now what do you think would be that of titration between strong acid and what weak base? Now whenever we have a strong acid and a weak base, the indicator you have to use is methyl orange. That's the indicator you must use. Now when we have weak acid versus strong base, you can draw it in the comment section if you know it. So when we have it, the indicator you must use is what? Phenolphthalein. That's the indicator you must use. So that's just what. Now when we have weak acid and strong base and weak base, if you look at that, that is weak acid, weak base. So that one, it doesn't have any what? No suitable indicator. So it means you cannot use any indicator for it. So no suitable indicator. So that's just it. So those are part of the things you need to know as a Jambite. Let's still move to another aspect. We don't have much time before the network palaver start again. So we still have some aspects. I'm just thinking of the topic I can teach you. Now we have method of collecting gases. We have what? Method of collecting gases. Method of collection of gases. I have moved to practical chemistry like that. So method of collection of gases. Now we have three methods. One of the methods is upward delivery or downward displacement of air. I'm going to tell you the meaning now. Now, this method is used for for gases that are what? For gases lighter than air. That is, they are very, very light than air. Now, example of such gases is nitrogen, ammonia, etc. But most of the time we don't use nitrogen. We cannot use nitrogen because we have other properties to use nitrogen for. So just know that under this example, the main gas we normally use is what? Ammonia. Now, this is how it looks like. This is how upward delivery or downward displacement looks like. Upward delivery means the gases is going to be taken like this. The delivery tube will be in this way. Now, if you look at it, the gas will go up like this. I hope you understand. So that's why we call it upward delivery. Why the air is going to be coming downward? That's why we now say downward displacement of air. I hope you get me. So that's the reason. So it's very, very simple. So that's the reason why we said what? The air, uh, the method is upward delivery and downward displacement of air. Now, don't forget the drying agent for ammonia, though it's not under this topic. The drying agent for ammonia is if you know it, you can draw it at the comment section. Is calcium oxide or quicklime. Please take notes. They ask you what's the drying agent for ammonia. It is quicklime. So let's continue. So that's the first method. We still have another method. Now guess the name of the second method. Now the second method will be opposite of this. You can drop it in the comment section. So the second method is downward delivery or upward displacement of air. So it is used for, that one will be opposite for this. So it's used for gases that are heavier than air. So this is how it will look like. Just bring it like this. Can you tell me the reason why we cannot collect? Okay, I'm still coming there. So this is downward delivery. If you look at it, the gas will go downward, while the air will be coming upward. That's why we said downward delivery and upward displacement of air. So example of gases used for this is chlorine gas. So we use this method for it. So I hope you understand. So let's continue. Because of our time, the ruler is not trying to. So, because we don't have a lot of time, so I don't know the network will be favorable this time. So let's quickly. So the last method is collection over water. Now, before we can collect a gas over water, it means that gas is insoluble in water. So it is used for gas that are relatively soluble or insoluble in water. So just know that there are gases that are slightly or insoluble in water. So there are many: nitrogen, oxygen, almost all those gases, SO2, all of them. So gases like that. Okay, I'm not sure of that SO2, but just know that nitrogen, oxygen, all those methane. So example like that. There are many. Almost all those gases, they are insoluble. So now can you tell me the reason why we cannot use this method for ammonia? So you can drop it in the comment section. You can try your luck before I say the answer. Now, the reason why we cannot use ammonia is that because ammonia is soluble in water, and we said, you know that I told you earlier that we use two gases for fountain experiments, which is NH3 and HCl. The reason why we use them for fountain experiments because they are extremely soluble in water, being a gas. And normally, gases are not supposed to be soluble in water, but they are like a guru. They just say, we will be soluble by fire by force. So they are still soluble. So this is the diagram, which will go like this. We draw the beef shelf. Let's draw it like this. You just go like this. Don't mind my diagram. So you would have seen something like this when you are reading. To no one will ask you to draw in your Jamb, but why they may say you should draw the preparation of a particular gas. So that's just it. That's the collation over water. Let me still go to another aspect. Which aspect should I go? Now, there's still another thing you need to know. Okay, in chemistry, what can I do? Which aspects should I go? Okay, in chemistry. I'm trying to look for a topic that is very, very, very important. Okay, now they may ask you which apparatus is used. So the apparatus, I will be talking about some apparatus. So okay, let me talk about gases. So if they ask you gas that turns lime water milky, what will be your answer? Which gas turns lime's water milky or chalky? What's the answer? So the gas that turns lime's water milky is what? Carbon dioxide or carbon dioxide, which is CO2. Do you get? So that's the gas that what turns lime water milky. If they ask you to write equation for the reaction, I can write it for you. This CaOH into bracket 2 is called the lime water. It's also called calcium hydroxide. So it means you will add CO2 to it, then it will give you CaCO3 plus H2O. So this is what forms the milky. Now you need to know that this milky will form in just what limited supply of CO2. After some time, if you continue to pass this CO2 to the solution, the chalky color is going to turn to colorless after some time. So it means I will still write this CaCO3 again. I will be having CaCO3 plus H2O. Now we had, okay, it should be CO2. Though I will still write H2O, but I just want you to know. So we had this water so that the equation can balance. So we have CO2 again. So after some time, so the solution will be what? Will be colorless back due to the formation of calcium hydrogen triazocarbonate 4. So that's it. Do you understand? So that's it. So this is another thing you need to take note of. Now they ask you which gas, the gas that rekindles glowing splinter, that rekindles glowing splints. So the gas that rekindles glowing splints is oxygen. So we have two gases. It's not only oxygen. We also have the nitrogen 1 oxide, which is also called laughing gas. The reason why we call it laughing gas is that if they release that gas, you'll just be laughing. That's why we call it what? Laughing gas. Do you understand? So that's a part of the things you need to know. Another thing is the gas that gives a pop sound. The gas that gives a pop sound. That gives a pop sound with glowing splints. That gives a pop sound with glowing splints. Glowing splints is like a lighter. If you bring lighter or a matches, so rekindles a glowing splinter means rekindles a glowing splinter here means that after you have maybe your matches after you have quenched it or extinguished it, it's still on again. So that's what they mean by rekindles glowing splints. Please don't be confused. Don't say that I don't know what's happening in that place. So that's it. Don't be confused, please. Please don't be confused too. So let's continue. Another thing you need to know is so the gas that gives a pulp stand with a glowing splint is hydrogen gas. So that's the gas that gives a pulp sand with glowing splint. So that's what hydrogen gas. Now they may still ask you. They may still ask you. So sorry about that. Okay. They may still ask you that. They may still ask you that which gas. So the gas. So the gas that turns lead to ethanoate paper to blue black. So if they ask you that, so the gas that is or black, I think it's black. So either way, so the gas is what hydrogen sulfide. So that's the gas that is responsible. Now, if they still ask you that which gas, the gas, so you can see that you need to know all these things that turns starch iodide paper to blue black. So the answer is a that is chlorine gas. Now you still need to know the color of chlorine gas. The color of chlorine gas is greenish yellow. Now they can still ask you that the gas that turns lime water milky, that turns lime water milky. Sorry, Jerry. That turns blue litmus paper red and later bleaches it. That turns blue litmus paper red and later bleaches it. So if they ask you that the gas that is responsible for that is what? Chlorine gas. Please don't forget chlorine gas new. So that's the gas that is responsible. So let's still go to another aspect. What else? What else? What else? Okay, let's go to flame test. So flame test is the color imparted by some metals. Though they don't have color, some metals don't have color ordinarily, but when you test them with fire, you will notice that they have a particular color. So it's not all the metal that imparts color with flame, but the common ones we are going to be looking at them. So the first one we are going to be looking at the calcium. I don't know why they like calcium. They like asking calcium and potassium. So the color for calcium is brick red. So please take note of that. For flame test, so it's not general test. For potassium, it is lilac. So please take note of that. They may also say lavender lilac. So number 3, that of copper is a bluish green. So I'm not going to be writing everything. I'm just going to be writing the ones I can remember, because I'm doing this offhand. So I'm challenging you. If I can do this offhand, you too you should be able to do it offhand. So lead, so that is a livid blue. So and so on and so forth. These are the major things they will ask you. They won't ask you more than this. It's very rare for them to touch other aspects. It is mainly calcium and potassium they normally ask. So they may change things. So just get your textbooks. All these things that we have done, take your textbook. I'm just doing a glance at the topics, so don't be confused. So we still have other aspects like we thank God for this service that we were able to do a lot of things. Now we still have some aspects. Another thing we still have is I still want to go to another topic so that you can gain a lot of things. Now we have what we call I'm just looking for a topic that is kind of very, very important that we can quickly do. So let's quickly do air pollution. So these are the pollutants that you need to know that are very common. So if they ask you which pollutants causes global warming, so the gas that causes global warming or greenhouse effect, it can also be greenhouse effect, causes global warming. I think the effect of global warming is greenhouse effect. So just say maybe and greenhouse effect. So that is a nothing but carbon dioxide. What else again? So the gas that causes blackening of the wall. That causes what? Blackening of the wall. Blackening of the wall. So it's what? Hydrogen sulfide. Please be writing something down, please, if you are watching this video. Hydrogen sulfide, which is H2S. As you am calling the name, you should know their formula also. They may not write their name like this, they will just write the formula. So the gas that causes what else again? So we are still in pollution. So that causes pollution. Let's just say it is pollution, not really air pollution. What else again? So we also have gases that causes depletion of ozone layer. That's also carbon dioxide. So depletion of ozone layer. Depletion of ozone layer. It is the effect of depletion of ozone layer that causes global warming. Ozone is O3. That is, ozone is an allotrope of oxygen. This is what O3. So it's an allotrope of oxygen. So we can form oxygen we can form ozone through oxygen by this method. I hope you understand. This is ozone, this is oxygen. So that's it. Ozone is O3, oxygen is O2. So let's continue. Which gases again? Then we also have gases that causes blood poisoning. So this gas is kind of compete with oxygen in the blood. So the gas is carbon monoxide or carbon dioxide. So either way you call it, or carbon monoxide. So which is also CO. Now let's leave the aspects. So we have what we call the extraction of metal. So let's come back to extraction of metal. Let's come back to extraction of metal. So we have two methods of extraction of metal. So metals, you should know that metals are cations. Now we have two methods of extraction of metal. We have chemical reduction and we have electrolytic reduction. Now we use electrolysis for metals that have high electropositive, that are highly electropositive. What I mean by highly electropositive is, I'm going to show you now. We have something we call activity series, activities or electrochemical series. So the acronym is, I will soon send you the video for electrolysis, so you will know the acronym. But popular science can make all zoo in the low humid, that's hydrogen, country copper, more satisfactory gold. Now this is it. Popular scientists, that's potassium, sodium, calcium, magnesium. So these compound, these elements, they are highly electropositive. So when you are extracting them, why do we need extraction of metals? The reason why we need extraction of metal is that most of these metals, they are highly reactive. So for us to get their pure form, it is very very rare. So we need to extract them to get the pure form of them. Hope you understand. Now the method of purifying, that is extracting metals that are highly electropositive, is using what? Electrolysis method. But for the rest of them, except aluminium, so aluminium is kind of the reason why normally we are not supposed to be using electrolysis for aluminium, but because we want to save a lot of money, so that's why we are using what? Aluminium. I hope you understand. So that's it. Now for the rest of them, so from year to year, we use chemical reduction. So chemical reduction is enough for them. I hope you understand. So chemical reduction is enough. But for the ones on the top here, we are going to use electrolysis. So you already know electrolysis, so that's all. So we will use the pure metal as our anode. Then we will use pure metal as our cathode. Then we use solution of that, what we want to extract. That's all. That is the salt solution of it. Then we use catalyst where necessary. For example, in terms of aluminium, the catalyst we normally use in its extraction is cryolite. We kind of use it so that it can reduce the temperature of aluminium, so that it can reduce the money we are going to spend to extract aluminium. So most of the time in extraction of metal, whenever they are adding impurities, addition of impurities in extraction of metal, addition of impurity in extraction of metal, most of the time whenever they add impurity, the reason is to reduce the temperature. So it's to what? Reduce the temperature. Don't mind my handwriting, that's very very small. I'm not, I didn't know that I can even create video tonight, but I just have to. So addition of impurities, so most of the time is to what? Reduce the melting point. That is to lower the melting point. To lower the melting point. That's the normal English we should use. Now, the process of extracting sodium, we call it Jamb process. Now, iron, this is iron, right? uh the purification of extraction of iron is it occurs inside the what? Blast furnace. So it occurs in what? Blast furnace. So after I did uh this glance, I will advise you to go over your notes, your textbooks. The place I didn't touch, please read them. Now let's go to reducing the chemical reduction. Now, in chemical reduction, this is what is happening. We make use of reducing agents in chemical reduction. We make use of what? Reducing agents. And the reducing agents we make use of is the reducing agents we normally use these are the common ones, and that is a carbon monoxide and hydrogen. Those are the common reducing agents that we use in chemical reduction. So we use carbon monoxide and hydrogen. Those are the two common reducing agents used in chemical reduction. Now, what else are we to touch again because of our time? Okay, I'm going to round up soon. Now, we have metals. They are common ore. The common ore for tin is cassiterite. That is the ore. Let me try to draw a table. The common ore for metal, let's draw the ore. The ore is the impure form of a metal. That is ore, the impure form. Now for tin, the impure form for tin is the common one is cassiterite. For that of iron, one of them is magnetite, though that's not the common form. So then we also have, when I remember, I'm going to tell you that if I still check, then we still have what else again? Okay, that of aluminium. They may ask you what's the common ore for aluminium. So that is bauxite. So you can add your own also. So that's it. Please take note of all these things. Don't count it as something that you can just keep in your strides. Please take note of them. So the common form for the ore of iron is hematite. So please take note of that. The common ore for iron, so is hematite. So that is the common ore, which is Fe2O3. So let's continue again. So these are the common ones. Though we have that of the common ore for sodium, for potassium, all of them they have their own common ore. But time will not fail us to be listing everything because we have a lot to cover. So just check your textbooks for more clarity. I'm just trying to touch some things that you need to know. Now, you need to know it that after extracting iron in the blast furnace, the quality of iron you will get directly is pig iron. When they say something is pig, you know that the animal called pig is dirty. So it means the pig iron is an iron that is formed directly from the blast furnace during the extraction of iron. So this iron it has a what? It has high level of impurity. That is, there is high impurity there. It is still dirty. So now after iron exhibits a little bit purification, is going to become a cast ion. After cast iron also will also have high impurity. It will not be really used because pig iron has a lot of impurity. You could hardly use them for things because you cannot use impure substance for metal or something. Now cast iron also, after exhibiting a lot of purification, is going to become wrought iron. Now this wrought iron is the best, and it has about 99 uh, purity. So it has about 99% purity. So if they ask you which iron is the purest form of iron during the extraction of metal, it is what? Wrought iron. So they can also put cast, but the most suitable is wrought iron. And if they say which one has a high level of impurity, it is pig iron. Hope you get something tonight. So we'll soon be rounding up. Now you should still know this. What else? What else do you still want to do? Okay. Now let me just touch this. These symbols. Delta H is called the enthalpy change. Now you need to know this, that delta H, when it is negative, the energy will be what? Energy will be released. And now, which type of reaction is this? When energy is released, we call them exothermic reaction. Please take note of all these things. Now, but when delta H is positive, that will be endothermic reaction. Endothermic reaction, that is, energy will be absorbed. So the reaction will be what? The reaction will be absorbed. The reaction will be I don't mean reaction, I mean energy. Energy will be absorbed. I'm just making a glance. Please check your notes. I hope you understand. So delta H will be negative, will be positive. When delta H is positive, just know that it is an endothermic reaction. That is, energy will be absorbed. What else again? Now we have something called delta G. So that is called the free energy change. So now, when delta G is 0, it has a meaning. When delta G is negative, it has a meaning. When delta G is positive, it has a meaning. When delta G is 0, you need to know what is happening. When delta G is 0, the reaction is at equilibrium. Please take note of this. The reaction is at what? Equilibrium. When delta G is negative, the reaction is spontaneous. That is, what does it mean by spontaneous? It means the reaction doesn't need external agent. So it's spontaneous or feasible. That is, it can occur on its own without external agents. So, but when it is delta G is equals to positive, so the reaction is non-spontaneous or non-feasible. So that's just it. So let's still move on. Now we have something we call the entropy change. So this is the entropy change. So it is the degree of randomness and disorderliness of a reaction. Now, between a liquid, solid, and a gas, which one do you think has the highest degree of randomness? Randomness means which of them is will freely move. Freely move means that which of them is going to freely move. Freely move means between liquid, solid, and gas, which one do you think will freely move? Will move freely. So the answer is gas. I hope you understand. Followed by liquid, followed by solid. Now it means if I have H2O, this is in liquid, it now moves to H2O, it now becomes steam. So if they ask you what is happening for the forward reaction, this is the forward reaction. You are going to say the entropy change increases because the liquid is lesser than gas in terms of entropy change. You know, I told you that entropy change is the degree of disorderliness or randomness of a substance or in a reaction, so of a system. So now, but if some the other way around happen, if it moves from a gas and now it now becomes a liquid, your answer will be the entropy change was decrease for forward reaction. But for backward reaction, reverse will be the case. Now, what if what if what if what if so another what if that you should know is, so I'm afraid we have to round up the video here, but let me see the place I can carry on. What if it is now from solid to liquid? So you still know that solid is lesser than liquid. So it means the entropy change is still increasing. I hope you understand. So solid to liquid means the entropy change is still increasing. Now, let's try to know how to get the equilibrium constant. So maybe this is where we are going to be rounding up. Now, assuming you have a reaction like this. Okay, let me firstly draw a pictorial, a like a dummy. If you have a diagram like this, a reaction like this, forward and backward reaction, and we have something like this, we have this, sorry, we have this, we have this, we have this. Now they now says you draw the Kc, that is the equilibrium constant for this reaction. Your reaction will be, this is how it will be. It will be the number of, it will be this over this, the products over the reactants. Are you getting me? So it will be products over the reactant, the sum of the products over the reactant. And now before you do an equilibrium constant, all of them must be in gaseous states. If one of them is not in gaseous states, it means if hasn't been, okay, let me firstly draw this first. So it will be C raised to power C into D raised to power D over A raised to power A, then B raised to power B. I hope you understand. So this is how to draw it. I hope you understand. So you will be putting the number of mole on top of it, like raised to power. There's a calculation for it. Then this place also you'll be making it raised to power for it. I hope you understand. So I don't mean we have a reaction like this: nitrogen plus hydrogen, forward and backward reaction, NH3, you have 2, we have 3 here. They now say you should draw the equilibrium constant for this. So it will be Kc you know that we have just one product, so it will now be NH3 raised to power 2 over N2. Now if you look at this N2, it has nothing in the number of mole, so it means raised to power 1. Then this one also, it has 3 as the number of mole, so just put what, H2 raised to power what, 3. So this is how to write equilibrium constant. Please take note of it. Take note of it. So take note of this. So we'll soon be rounding up. So don't say that you said that we soon be rounding up since. So it's because we have a lot to cover. Seriously, I can't lie. There's a lot to cover. Though we have done all the tutor has done all this, but because you guys joined the tutorial late, that's how we still have to do some recap. Because revision is very, very important for UTM. So what else should we touch? So we should be rounding up. What else should we talk about? Now, you see, you should still know this. In a okay, what do you think I should talk about? Okay, I'm just thinking of a topic that's very, very okay. Let's talk about water. So we have water. What do you know about water? We have two different types of water. We have hard water and we have the soft water. Now, what do you know about hard water? Hard water, they kind of had a good taste or a better taste. They are very, very pleasant to taste. They have a good taste, but they have disadvantage. They also help in building shell for organisms that have shells like snails. So they have advantages. Another thing is, but their disadvantage is that they don't form ladder easily with soap. So that's the reason why they must be softened. I hope you understand. And also, they also what? They causes what? Furing of K2. So these are the things you need to know. They cause what? Furing of K2. So salt water, we don't really have any much to talk about salt water. Now we have two types of hardness of water. We have two types of hardness of water. So we have temporary hardness and we have permanent hardness. Temporary hardness is the hardness that can easily be controlled by. So you can quickly stop the hardness of water, the temporary hardness, by just adding lime water. No, it's not really. That's the definition. Is but just by simple boiling. If you boil a water with temporary hardness, it is what? Boiling. It is removed by just boiling. Now, permanent hardness, you cannot remove it by boiling. The only way you can stop permanent hardness is ion exchange resin. That's the method. The second method is addition of caustic soda. So we have like 3 methods. Addition of caustic soda, which is also what? Sodium hydroxide. Another method is addition of washing soda. So it has become two soda like that. One is caustic soda and one is washing soda. And what is the formula for washing soda? That is Na2CO3. So we are rounding up soon. Though the thing is just getting long, very long. Now if they ask you what ions causes hardness of water, so the ion responsible for hardness of water is Ca2 plus and Mg2 plus. In some textbook there may be more than these two. Now since these two ions causes hardness of water, now which one is now responsible for temporary hardness and which one is responsible for permanent hardness? The one that is responsible for temporary hardness is CaHCO3 into bracket 2, since you know that calcium and magnesium causes it. So the second one you are still going to be writing, it will be what? Mg. So just replace this Ca with Mg. So it will now be Mg into bracket HCO3 into bracket 2. Similarly, this way also, when you are writing that of permanent hardness, it will be like Ca, then you just put SO4 here. And don't forget our rule, it remain magnesium, right? So the second one that causes permanent hardness is what? Just put Mg there. So these are the two things that causes such hardness. So this CaCSO4, they causes permanent hardness. CaHCO3, they cause temporary hardness. Why? So that's just it. So, and you should know their name: calcium hydrogen triisocarbonate 4, magnesium hydrogen triisocarbonate 4, calcium tetrasulfate 6 salt, and magnesium tetrasulfate 6. So that's just it. So please take note of all these things. If they now ask you what is the test for water, what is the test for water? So if we don't do all the water, so test for water, we have test for water. Now, normally we have what we call anhydrous copper 2. When they say something is anhydrous, anhydrous means that thing is dry, it has no water or very very little water, even no water at all in it. So we have anhydrous tetrasulfate 6 salt. So normally this salt is white when it is anhydrous, but when it becomes hydrated, that is when water gets to it, so it when it is become hydrated, maybe plus water, so it becomes blue. So if they ask you which compound is responsible for changing anhydrous copper 2 tetrasulfate 6 to blue, so that compound is water. Just know that. So we have to test for what? For water. So the second test is anhydrous yes, anhydrous cobalt 2 chloride paper. Cobalt what? 2 chloride paper. So I think it's like this. Yes. So this one, the compound form after water gets to this one is hydrated. It becomes hydrated copper 2 tetrasulfate 6 acid, that is CuSO4.5H2O, and before it is what? CuSO4. So after it is hydrated, it will be CuSO4.5H2O. But here, this one I think it will be CaCl2.2H2O. You don't really need the compound, just know the color change. Now this compound is blue when it is anhydrous, that is when water has not gotten there. But when water get there, it's going to change to pink. Please note the color change. For copper 2 tetrasulfate 6, it will change to blue from white. For cobalt 2 chloride paper, it will change from blue to pink. So they are somehow similar. So there is where we are going to draw the curtain for today's revision class. So that's that. So bye. So I will like you to drop a lot of comments where necessary when you watch this video. So I hope this video be of great importance to you. In Jesus' name, amen. So all our effort will not be in vain over you guys. You will succeed in Jesus' name, amen. Thank you. That's that for this video. Bye.